Google's web crawler indexes over 200 trillion web pages. That's roughly 35 pages per person on Earth. Here's what 90% of engineers get wrong when designing a web crawler. They focus on speed, not politeness. We'll see why this matters when we discuss scaling. Now that we've set the stage, let's define the scope. Functionally, we need to extract and index web pages, follow links, and handle different content types like HTML, PDFs, and images. Non-functional requirements, scalability, politeness, avoiding overloading servers, and freshness of index data are key. What clarifying questions should you ask? First, how often should we re-crawl pages? Second, how deep should we crawl, limiting the number of hops? This brings us to a crucial challenge, capacity planning. Let's assume we want to crawl 1 billion pages, averaging 1 memory dollar bytes each. That's 1 petabyte of storage. If we re-crawl weekly, we need to download roughly 140 terabytes per day. Assuming a 24-hour crawl, that's about 1.6 gigabytes per second of bandwidth. At 1 MB layers per page, that translates to roughly 1,600 pages per second. Stop. Think about this. With the foundation in place, let's tackle the high-level design. We'll separate the write path, crawling and indexing, from the read path, serving search queries. The write path starts with a URL frontier, which feeds URLs to crawler workers. These workers fetch pages, parse content, and extract new URLs. A robots.txt parser ensures we respect website rules. We use this because it prevents us from being blocked. The read path involves indexing the crawled content for fast search. A CDN caches frequently accessed content. Note the separation of concerns here. Now we understand the high-level design, let's dive into the core logic. The URL frontier is a critical component. It's essentially a priority queue of URLs to crawl. We might be tempted to use a simple queue, but that doesn't account for politeness. Instead, we use a hierarchical queue, prioritizing URLs based on hostname and crawl delay. This is where most people go wrong. The crawling algorithm itself can be breadth first or depth first. Breadth first ensures we discover more sites quickly, while depth first explores individual sites more thoroughly. Your interviewer might ask, what happens if a crawler crashes mid-crawl? The key is idempotency. Each crawl task should be self-contained and retriable. This is where a URL frontier comes in handy, as it allows us to resume crawling from where we left off. Now that we've covered the core logic, this sets us up for the deep dive into the data model. We need to store crawled content, extracted links, and metadata. What database should we choose? While a relational database like Postgres could work, a NoSQL database like Cassandra is better suited for the high write throughput of a web crawler. We use Cassandra because it's designed for high write volume and scalability. The schema might include fields like URL, content, HTTP status code, last crawl date, and extracted links. Deduplication is crucial to avoid indexing duplicate content. Having locked down the data model, we need to address scaling and performance. Caching is essential for reducing latency. We can cache frequently accessed pages in a CDN or a distributed cache like Redis. We use Redis because it provides fast in-memory access. Replication ensures high availability. We can replicate the search index across multiple nodes. Sharding allows us to distribute the crawling workload across multiple machines. DNS resolution can be a bottleneck. We can use a local DNS cache to reduce the number of DNS lookups. Rate limiting is critical to avoid overloading target servers. We can implement a token bucket algorithm to control the crawl rate. Remember the 1,600 pages per second we calculated? This is where it matters. To handle that volume, we need to distribute the workload across multiple crawler instances and optimize our network configuration. This brings us to a crucial challenge, reliability and operations. We need to ensure the crawler is fault tolerant. If a crawler worker fails, the URL frontier should automatically requeue the task. Monitoring is essential for detecting issues. We can monitor metrics like crawl rate, error rate, and CPU utilization. Alerting allows us to respond quickly to problems. We can set up alerts for high error rates or low crawl rates. A retry mechanism is needed to handle transient errors. We can implement exponential backoff to avoid overwhelming target servers. An experienced interviewer will probe, what happens if the monitoring system fails? The key is redundancy. We've covered a lot of ground. The core trade-off is completeness versus freshness versus load on target servers. We gain completeness by crawling more pages, but sacrifice freshness and politeness. Potential bottlenecks include DNS resolution, network bandwidth, and database write throughput. Next steps might include implementing adaptive crawling strategies or adding support for JavaScript rendering. Remember, politeness is paramount.
Join our community of engineers mastering software engineering, algorithms, and technical skills. Subscribe to stay connected and never miss a tutorial.